Hello, everyone. Welcome to this colloquium. It is my great pleasure to welcome Piyali today here for this colloquium talk. She is currently an associate professor at IIA Bangalore, and her primary interest is in the application of computational magnetohydrodynamics to the study of the sun, from solar interior to the corona, including quiet sun as well as eruptive phenomena. Some of her recent contributions have been to show how delta sunspots can form and flare repeatedly, releasing solar-like energies, and demonstrating the 4-ingredient criteria for generation of solar plasma jets called spicules. Lately, her interests have diversified into other astrophysical MHD domains, including compact star dynamos and accretion disks. So a little bit about her background. She has done a master's and PhD in physics from IISc Bangalore. Her PhD thesis was on flux transport dynamos and solar cycle prediction. Subsequently, she held postdoc positions at TIFR Mumbai, Nordita, Stockholm, HAO Boulder, and University of Oslo. And since 2015, she's a faculty member at IA. So she's also one of the developers and maintainers of the open source code called Pencil Code, which is hosted at GitHub. She also serves on the International Pencil Code Steering Committee, and she has incorporated many new modules to Pencil Code to make solar MHD simulations more realistic. She is also a member of VELC science team at IA. This is for the VELC coronagraph, which is to be incorporated on Aditya L1, which is India's first solar mission to be launched soon. So welcome, Piyali, and look forward to your talk.
Yeah, thank you, Pallavi, for your kind words. And I'm very happy to be here. I'm having a wonderful day so far. Today I would like to share with you one of our recent work about which we are very excited. So this is also part of my student Shohel's PhD thesis, which he has already submitted now. So he's also there at the back. And in the team, so you see we are 7 people, and 6 of us are actually from solar physics background with no idea about experiments or fluids whatsoever. The only person who has some idea of doing experiments or has worked with his hands is Murthy. So he is a faculty at Azim Premji University now, but his background is also semiconductor physics. So none of us actually knew any laboratory fluids. So that's where we started from. So by and by, and if time permits, I'll tell you the backstory of this work. Let me just start with what are solar spicules. So you see,
you're okay with questions
in the middle? Yeah, it's fine. Yeah, it's okay. Yeah, please just stop me and ask if you wish. So you see that there is this really silly cartoon of a very simple cartoon of the solar atmosphere here. As you know, the visible surface is the photosphere, and then you have a thin layer called the chromosphere. And then you have a even thinner transition region and a corona, and the spicules are basically jets which originate in the chromosphere and transition region of the sun. And this is the Earth to show you the scale. And there are millions of them on the solar surface, so it's like a grassland of them. Only thing is that since these are jets, so they move up and they have to fall back down, so they operate under ballistic forces. And they have these physical characteristics. So what is important is that the aspect ratio is really large, so they are like thin jets. And they move up at these speeds, 20 to 70 kilometers per second, which basically means they are at speeds which are slightly larger than the speed of sound in the solar atmosphere. Of course, the solar atmosphere is highly stratified, so the speed of sound also changes as you move up. But even though it changes, the speeds basically remain hypersonic, if not supersonic. And as you know, that the solar plasma can be sampled by looking at different spectral lines. So you can, spectral lines which basically sample different temperatures of or different heights in the solar atmosphere. So for example, the chromosphere can be sampled by the H alpha line, which is in the red spectrum, or even the calcium lines, which can be in the UV. And these are what are known as cooler lines because they sample plasma at 15,000 Kelvin. So it's cooler by the solar standard, because the hotter channels, for example, the UV lines, the ultraviolet lines, for example, the silicon and the magnesium lines, they sample temperatures of say 80,000 Kelvin. So then there are cooler lines which sample the plasma near the chromosphere, and the hotter ones which correspond to the plasma in the transition region and the corona. So they are seen in different lines. And if you see them on the disk, you will see them as dark regions because you see them in absorption. Whereas if you see them on the limb, they'll appear on emission because, of course, there is nothing in the background. And yeah, so they are prominently observed in emission lines inside, especially coronal hole regions, for example, here, where where the fast solar wind essentially originates. So with this background, so yeah, here is another movie. So this is a highly imaged, processed movie from an instrument on board the SDO spacecraft by NASA. So this is the transition region of the sun, and here you see these jets. They look tiny because look at the scale here, but actually their heights, they can be up to 20,000 kilometers in height. And why is it significant and why should we study the spicules? One is that they can play an essential role in the mass and momentum transfer to the solar wind. So how is the solar wind accelerated, and why is the corona so hot even in the coronal holes? The darker coronal holes is also a mystery. So it is envisaged that even if 2% of the mass flux that you can calculate from these emission lines in the spicules can go up, they can account for the entire mass supply to the solar wind. This is a very old calculation, but it still holds now. So that's why all the more reason that the spicules and their dynamics should be studied in detail. So of course, the next question is, what is the origin of this forest of spicules, not one or two spicules? Because we are not looking at just a particular kind of spicules, but the whole forest, and we want to know how that whole forest comes into being. And the sub question is, what are the different generation mechanisms? Are there several, or is there one mechanism which can explain everything? So there are these different mechanisms that people have again put forward. One is the MHD shock waves, magnetic reconnection. P modes are essentially the acoustic modes of the sun. And then comes the Alfvén waves. So we don't know if all of them play a role, and does each mechanism give rise to a different kind of spicule, or what is exactly that is happening? And should we classify the spicules? Is there a way to classify them on the basis of their height, speed, how they look, and how should we go about doing it? So now there's again a little bit of a history based on observations from a Japanese spacecraft known as Hinode that was launched in 2006, I think. But that has so far given us really high resolution images of spicules. So using Hinode data, so people found out that there are two kinds of spicules on the basis of the kinematics. So there are one kind where the spicules follow a parabolic trajectory in time. So basically this is the height and time. So it is as if you are looking at the image through a vertical slit, a slit perpendicular to the surface of the sun, and you are just recording whatever you are observing, and then you see the spicule tip goes up and it falls back down. It is a parabola, and which basically means that these are ballistic, governed by the gravity. And however, there is other kind where you see these streaks. So they go up, but they don't see anything falling back. So what happens? I mean, there is something missing. So then people classified it in 2007 in terms of type 1 and type 2 spicules. So only using the Hinode data, which is actually looking at cooler channels, the cooler plasma. So it doesn't know what is happening at other temperatures, or if the plasma is undergoing any other heating mechanism. Hinode doesn't know. It is only observing plasma at a particular line, that is the calcium line. So only on the basis of this line, there was this classification that was made. And then it was called type 1 and type 2. The type 2 seemed to have higher speeds, and they were only seen for a little while in the calcium channel, not for a long while, because they'll just go up. So people thought these are like more energetic than the type 1 spicules. However, with the advent of other telescopes, for example, IRIS, which could observe the spicules in hotter channels as well, they found that in Hinode, the type 2 spicules, which had a linear trajectory in space and time and height, they would also have actually a parabolic trajectory if you were to observe the hotter plasma. So the idea was that maybe the cooler plasma is getting heated up in some way and vanishing from the cooler channel. It is going into a hotter channel, and it is doing the same thing all over again. It's just that we don't see it in that channel. Fair enough. Now, there were another group. So one was this European group that I spoke about earlier. This was a Japanese group, and they used the same data set, the same Hinode data set. And what they said that, look, you are looking at a 2D image, and the spicules have 3D dynamics, right? And if you're observing it through a slit, the spicule in the line of sight could just do this and be away from the slit. So what you're looking at, that there is no distinction between type 1 and type 2, but it's just that the modes of oscillation of the spicules make it vanish. So that is another argument about why this type 1 and type 2 may not be the most correct one. But to this date, I mean, most of the solar community actually sticks to this type 1 and type 2 spicule. So whenever you say you have done a spicule simulations, the observers come and ask, is it type 1 or is it type 2? Then you don't know what to answer. Anyway, so moving ahead, so the existing idea is that there are type 1 spicules which are shorter, less than 10,000 kilometers, and they have lower velocities. And they are formed by magnetoacoustic shocks, which are basically formed by leaking sound waves from the vibrating sun, right? The sun vibrates because of the solar convection creates a lot of these sound waves which are trapped, and then that is undulating the entire solar surface, right? So that are known as P modes. And those P modes, some of those P modes, they leak out into the atmosphere, not all, only some of them, when their frequency is greater than a certain threshold. And those leaking P modes can form MHD shocks because there is magnetic field in the solar atmosphere. The sound waves interact with the magnetic field and form MHD shocks. And there are other mechanisms like Lorentz force siphon flows that were proposed by different other groups. Now, type 2 spicules, so this they believed is more energetic, so there has to be some other mechanism. So sometime back in 2017, there was a paper in Science which basically says that the magnetic fields, when they reconnect, they form a whiplash kind of an effect. And that whiplash would, spring the plasma into the solar atmosphere, and it can go much higher than the normal type 1 spicules. So the type 2 spicules have a totally different mechanism. So now we thought we will give it a fresh look and see what we found. So we actually started with this visual similarity between the Hinode spicules. So you see these jets here, and basically a dish full of paint, and kept on a, yeah.
Yeah, just a question about your previous slide. I mean, you had mentioned that there are two types, and one group claimed that it might be just less because of the line of sight. Is it possible to look at? Is there any correlation between specules which are nearby?
Sorry, is there any correlation
between those specules which are nearby? I mean, using
nearby.
Yeah, and using that, can you distinguish? Can you say something about the line of sight? I mean, if you are looking at one, but if you can look in the surrounding and distinguish them.
Okay, one thing is to look at Doppler shifts of these in this movie. So, for example, let me see if this movie runs again. So you see, so if you look at Doppler shifts, then you can see, something is coming towards you or away from you. But then the Doppler shift measurements from the IRIS spacecraft that looks at these hotter channels. Right now, the resolution is very, very poor. So it is not clear. I mean, at least to me, that if that particular spicule is going away or into the. It requires more careful observation. But yeah, let me confess that we have not done the observation. It requires really involved observational analysis. But Doppler effect is something. Doppler shift is something you could use to distinguish if it is going away from the slit or not. Rama.
Suppose you didn't worry about whether it's type 1 or type 2, you just plot the distribution of upward velocities, PDF. Then do you see two humps like at 20 and 60?
No.
You see a continuum.
Yeah. You see a sort of a high distribution is sort of like a power law. So we have also done that. Maybe later on I will show you. So there is no bimodality. That is the thing. Okay, so yeah, so we decided to look at it in a totally different way. So there's, you will probably appreciate that there is visual similarity between this astrophysical phenomena here and this phenomena in a lab, which is basically a popular science experiment where you place some paint, which is a viscoelastic fluid, and you do Faraday, you do a Faraday excitation on it. So basically, you turn on the music, so to speak, so bass frequencies, and then this is what you see. So then we decided that perhaps this visual similarity can be explored some more. So how do we do that? So one of the things that is striking that we found is we can still use the magnetohydrodynamic approximation for the solar plasma. And the viscoelastic fluid is also governed by different models in polymer physics. And if you look at the mathematical similarity between the viscoelastic and Maxwell stress, that is actually striking. So maybe there is something to it since there is mathematical similarity. So spurred by that, we decided to do some laboratory experiments and numerical simulations, because observations we cannot control. So we decided we'll do numerical simulations because we can control a lot of parameters here, and we can see if we can make a similar phase space in the laboratory as compared to the plasma. So that was basically the goal of this study. But actually, I am presenting this slide at the beginning, but this actually became clear to us at the end of the study. But it is not pedagogical, so I'm just showing it at the beginning. So to start with, we did some very simple back of the envelope scaling and similitude to look at the scaling look at these properties of these jets essentially. So we take the jets and then we look at its width, length, and velocity, and also the jets in the lab, where we excite it by a function like this, driving forcing like this, a cos 2 pi f naught t, where f naught is 30 hertz, which is a low frequency. And with these parameters, we can create some non-dimensional parameters, for example, the aspect ratio of the jets. And then we can also talk about the Froude number. The Froude number basically is, I don't have to tell you people, is the ratio of the inertial term to the to their gravity in the problem. So basically tells you about the importance of gravity or the surface gravity waves. And then we can compare the acceleration of the jets, the upward acceleration of the jets to the local gravity. And we can create another non-dimensional parameter, for example, which is the driving frequency multiplied by the lifetime of the jets. So the lifetime is basically the time the jet takes to go up and then fall back down. And I hope you will appreciate that all these parameters, they fall in a similar ballpark range. So then that is quite encouraging that there is some amount of scaling similarity between the two systems. And if we stick to this kind of 30 hertz around frequency in the lab, that is probably ideal to compare with the solar plasma. So again, we go ahead, and a little bit of aside on Faraday excitation. And what is known as nonlinear mode coupling. So these experiments have, they are not by us. They have been reported long ago in this paper here. So these have been done by silicon oil in a dish, and then it has been subjected to different driving and different frequency. And what these authors found is as you increase the amplitude and the frequency, you see these different pattern formations. So the surface is breaking into patterns. And this formation is basically due to what is known as three-wave resonant mode coupling, right? So there are these subharmonic modes, harmonic modes, which are coming in, they combine and they give some other mode. So they are forming all these patterns here. And such things can be also modeled. The surface, for example, where zeta is the height of the free surface from the bottom, can be modeled in terms of what is known as a Matthew equation, which is an equation for a damped driven oscillator. So you change the parameters and then you will see that which mode is which modes are allowed and which modes are not allowed. So as you increase the energy, more and more modes are allowed and more complex patterns can form. So now what happens if you increase the amplitude quite a bit? So if you do that, you see there are not just patterns, but also jets. So there are these ridges that form. These ridges, they collide and they gives rise to these jets. So this is an experiment that we did with a kind of a viscoelastic fluid known as PVA, polyvinyl alcohol. So this is also used for making photographic films actually. So we prepared, we iodinated it so that there is color, and also we could see the stretching in laser experiments.
Yeah, the boundary, does it have any effect on the
So the boundary has the effect in forming the patterns only when you are at low energies, only when the amplitude of driving is small. As you increase your driving, you see more and more smaller patterns, right? After some time, it doesn't matter what is the shape of the boundary. So you take a cylindrical container, you take a square container, it doesn't care. The patterns will look the same. I mean, you will probably have to do more structure analysis, structure function analysis and things like that. We have not done that, but at least to the eye, it seems it doesn't care what the boundary is after a certain time.
So how big is this container and how fast are you shaking it?
Yeah. So this is also still at 30 hertz. And the container is 10 centimeter in diameter. And they were, we are not showing you, of course, the entire, this is cropped. So they were like many, I don't remember how many, but the wave number was quite high. But it's 30 hertz frequency so far. Okay, so why are they forming these jets? So there was this another experimental paper long ago where they said that this surface here basically becomes singular, develops a singular curvature. And when it develops, because there are these surface gravity waves sloshing around the fluid, the curvature can become singular, and then it would the surface will try to straighten, and then that would give rise to a jet. So we think perhaps that is also the case in the several jets. So this was only for a single jet. So it basically says that the interface develops a high curvature just before the jet is produced. But in our case also, where there are several jets, we believe that such a thing might be occurring. So now after this aside on the fluid, we want to compare also with the numerical experiments. So we go back to our numerical model of the solar atmosphere. So basically we have no convection zone in the sun so far. We only have the little bit of the photosphere and below, chromosphere transition region and the corona. And we use a 2D box. We don't do 3D. 3D simulations are really complex, time consuming, and we are poor people. We don't have that much of computing time. So we do 2D. So it's a big enough box, 18 megameters, 18,000 kilometers by 18,000 kilometers in the horizontal and 44,000 kilometers in the vertical. So which basically means we go really high into the corona. And here on this entire domain, we impose a vertical magnetic field. The reason is that there is magnetic field in the corona. And since this is a 2D model, and we cannot run it for a very long time, so we don't have any dynamo in it. So there is no consistently produced magnetic field. But since there is, we are talking about the coronal hole region in the poles of the sun, for example. So there the magnetic field is expected to be vertical. So we impose an artificial vertical magnetic field in the domain. And here are some techniques, basically, you don't have to worry about that, like having semi-relativistic Boris correction and radiative transfer and anisotropic thermal, Spitzer thermal conduction, but I could talk about it if someone is interested. So these are all, these modules are all available in the pencil code. And basically, we have a sponge layer at the top of the domain. So the idea is that when you drive the domain, there will be a lot of waves which will be produced. The waves will travel up, but we don't want the waves to reflect back. We want the waves to just escape. So we basically artificially absorb them in the sponge layer. So this is the basic idea, and this is the stratification. So the density stratification, which basically decreases with height, and the temperature increases to about 1,000,000 Kelvin. So there is a spread here because this has been for different horizontal elements, they are different. So there's a spread, but essentially the mean is the same. So this is our model, and this we are going to basically drive. So we will do parallel experiments. Yeah. How important is the convection? So it is important in the sense that it is carrying most of the heat flux along the magnetic field lines, right? So if you have a region where you suddenly have heating, right? So you will expect that the heating should, the heat should only flow along the magnetic field line rather than perpendicular to it. So this is how important is for the spicules. Yeah, I don't know. I don't know how important it is for the spicules, but then since we are looking at wave propagation and things like that, we basically included it in the model already. But probably if we switch it off, we have normal thermal conductivity, the isotropic one, even then we would have spicules. But may not, but some things may change.
What sets the driving frequency and how does it relate?
In the sun?
Yes, and how does it relate to the natural frequency of those P modes?
So the P modes have, so in the convection zone, if you observe the granulation pattern, they have a typical time period of 5 minutes. So which is known as the solar 5-minute mode. So basically the dominant frequency is 5 minutes. So we will try to do our experiments, most of our experiments, such that we focus on that 5-minute periodicity thing. But it is quasi-periodic. It is not exactly harmonic, of course, because there is a, it's not a very sharp peak. It's a very blunt continuous power spectrum and the granulation pattern. So that is the normal mode of the sun that we will try to use everywhere. But in the atmosphere, there are other frequency, for example, the 3-minute mode. So there are other high frequency modes that are observed. But if you observe mainly on the photosphere, the dominant one is the 5-minute.
Natural frequency
of the it's basically the lifetime of the granules. So the granules form and then they die, they collapse, they do all sorts of things. So when I say 5-minute, it is also the typical lifetime of the granules. It is also the frequency at which these granules are breathing. So if you see the distortion of the solar surface caused by the convection, so this distortion is also breathing at this 5-minute frequency. The spicule lifetime is little longer, like it could be up to 14 minutes or, just go up and fall back down. But there is a 5-minute frequency, in the formation, one after another. If the spicules are forming, they are forming at this 5-minute thing, but the lifetime is longer because it has to fall back. Okay, so we basically do parallel experiments in both systems. So in the lab systems, whatever we do in the, the lab, of course, the frequencies are different, the scales are different, but the same tuning we will do in the numerical experiments. So what we do is each system, we will collect an ensemble of experiments by varying the frequency of the parametric driving. So basically this F0 at the bottom boundary. So both numerical, the plasma and the lab, we drive it with this harmonic excitation. Of course, for the sun, the frequency is in the millihertz range, like 5-minute corresponds to 3.3 millihertz. So we will only work in the millihertz range, whereas in the lab we will work in the 30, 50 hertz, that sort of range. And then we will ask the following question. So at what minimum value of this driving amplitude for any given frequency do we obtain a forest of jets in either system? That is the question we want to answer. And basically we do these parallel experiments. Now, before we do the experiments, you have to define what do we mean by forest of jets. Now that is, yeah.
How do you define the hertz or range from 10 to 100?
It could. So you remember I showed you this table initially where we were looking at these scalings, right? So there we found that from our initial experiments, we found that if you have to match this aspect ratio of these jets and the ratio of this driving, the forcing to the local gravity. So one of the frequencies is this 30 hertz. There may be others, but we found that. So we said that we will do at 30 hertz. But then when we do these parallel experiments, like I said, it is for a given F0. So you can vary F0 in a range and you can make a phase space, right? So, okay. So now in either system, we have to define what do we mean by forest of jets. Of course, like the sun, we cannot have million jets. So we just say that at least we need in 10 cycles, 10 driving cycles, we need at least 4 jets which go beyond a certain critical height. They cannot be tiny, they have to be longer than a certain height, and they have to have a certain aspect ratio. So the aspect ratio width to height has to be lower than 0.5. I mean, okay, aspect ratio depends how you length to width has to be greater than 2 or width to height lower than 0.5. So there has to be a certain number and a certain aspect ratio, and that's my forest of jets in both the systems. So I show this experiment with solar plasma here. So there are 3 experiments, 3 different experiments. We are driving at this frequency. So here we are showing, so for the sun, we are using this solar plasma, we are using this 3.3 millihertz. And there are 3 different forcings we have used, 3 different A. And you see in one case, the driving is less than a threshold. So let me try to run this movie for you. Yeah, it's running now. So there are no jets here. Here, the jets are barely crossing this dashed line, which is the threshold, whereas here the forcing is greater than a threshold, so we have a forest of jets, right? Similarly, in an experiment, we basically use a particular, again, a viscoelastic fluid that we prepared, known as the polyethylene oxide. Yeah. This threshold, that is what I said. It's a bit arbitrary, but once you fix it, you have to fix it for all experiments that you are doing. So I could say that instead of 7 megameter, I'll say it is 5 megameters. Then I'll have a different curve. But for every experiment, I have to stick to the threshold being 5 megameter. It is arbitrary. But once I fix it, it has to be same. Okay. So then, yeah.
In the previous one, why are the jets in the same position?
Oh, why are they in the same? I think it is because, that is, no, they are coming in different positions, but here we are basically also have a spatial thing which corresponds to the size of the granules. A spatial kx, which corresponds to the size of the granules, and it is a very regular thing, right? It's a cos kx kind of a driving. So you see this regular pattern, but if you have a quasi-periodic thing where it is, you won't see this regular pattern here. But yeah, we had no other way because we wanted to test at fixed frequencies. So only way is to take this harmonic thing. Okay, so now back to the fluids. So we take this viscoelastic fluid called the polyethylene oxide, which I think is used in different things like shampoos and shaving cream, for example. So we prepared this, for example, 500 ppm concentration a sample in the lab, and then we subjected it to different forcing, which is given in terms of the local gravity here. And if I run it, so the dashed line here basically shows the threshold, which is same. And you will see only in these two cases on the right, you'll have to stare at it and watch it several times to make sure that there are more than 4 jets which are crossing this line, and they are thinner to make sure that it's actually a forest of jets. So we basically, this is what we do, and so then we plot our findings. So we have a huge number of experiments now, both in the numerical case and in the polymeric fluid case. So each point here is basically an experiment. And when it is a closed symbol, it means that we found a forest of jets, and open symbol means there were no forest of jets. So basically, at each frequency, we sort of do a bisection method to find out what is the threshold. So we approach from below, and we see that there are no jets, and then we increase the driving a little bit. There are jets, and they keep decreasing the driving. So for each frequency, we actually end up doing 5-6 experiments, and when we see where is the threshold of that. And then we connect all the points of the threshold, and you see a certain pattern here. So this pattern in the fluid case is quite well known actually. So it follows a power law, frequency to the power 4/3. And it is possible to do some dimensional analysis to prove why this is the case. So actually for Faraday excitation, this is observed. But surprisingly, we also observe it when we increase the amplitude and we have jets. So that is surprising for us that even now this 4/3 power law is obeyed. However, for the solar case, there has not been any such experiment. But you see that roughly we can divide these regions, each phase plot, into 3 regions here. So there is region 1 in which it becomes increasingly difficult to produce a forest of jets as you decrease the frequency. Whereas in region 2, you see that as you increase the frequency, it becomes more difficult to produce the jets. So the threshold amplitude is increasing. And in region 3, it has a different behavior. the solar case and the polymeric case. But overall, at least in the region 2, they have a qualitatively very similar behavior. So we feel that the threshold acceleration versus frequency, driving frequency, has a similar behavior in a particular frequency range in both the polymer as well as the solar plasma case. So once you have this scaling plot, so what we basically find from this is what you need to produce a forest of jets is large amplitude quasi-periodic excitation. I'm calling it quasi-periodic here, but we have done the experiment with harmonic cases. If we combine some of the harmonic cases, we also get jets, so I call it quasi-periodic. But one of the requirements for producing the jet is large amplitude quasi-periodic excitation, because there exists a threshold. Only above this threshold, you will form jets, and below the threshold, there are no jets. So this behavior is similar in both systems. So here I call it the third, because the first two similarities in the fluid system, in both systems, is fluid and gravity. So one is fluid, one is gravity. So the third similarity is this large amplitude periodic excitation.
So in R2, in the solar case, there are only like 4 points, right? Have you measured the power law exponent?
We have not. It was probably more than 4/3, but we did not give it here because we need to do more work here to actually, this is totally unexplored. Nobody has done it systematically. So one has to do that more systematically.
So when you say they are similar, it's just in the sense that it is increasing with frequency.
It is increasing with frequency. And there is a threshold, the existence of a threshold, right? So only above a certain amplitude, if you take a particular frequency, only above a certain driving amplitude do you see jet, not below that. And that behavior is also very similar in both cases. So for example, here in the fluid case at very high frequencies, where the jets become really thinner and thinner, it looks, that is also a regime which is really exciting to observe. You see that here, even if you increase the frequency, we didn't find, at least till, we went up to 105 hertz, we didn't see any change in the threshold driving. So that is something we did not explore any further, because there was not much parallelism to explore with the solar case, not yet. So we basically said that, look, there is this existence of a threshold which is same in both the systems, apart from both being fluid and in presence of gravity. Okay, so yeah, Shamriddhi.
So for example, in the solar problem, if I'm sort of modeling MHD, so I have the property of the fluid itself, I can control, let's say, with the magnetic Reynolds number or Prandtl number or something.
Yeah,
in
the
your
stratification you can control.
And stratifications. So if I were to change this curve, right? So on the left side, I can probably either change the stratification or I can change the Prandtl number, something. There might be a qualitative shift in this. For the polymer case, what's the analog for that?
Oh, yes. So this one, for example, was, I think this curve we did with this, the concentration, the polymer concentration, for example. So I think we did this experiment with all the points for this was with, say, 50 ppm. 50 parts per million.
So if I were to do with 100
the
ppm,
concentration,
it will shift.
It will shift
with the scaling.
It will shift with the scaling. I think we did have some plots for that, but I don't remember what happened. Curious, but it shifted. It changed when you change the concentration.
Because some years ago, I think Ramami have also worked on this, where they were exploiting, in the turbulence jargon, a lot of the formal similarities of structure of viscoelastic fluids and MHD in terms of the stresses. So I was just wondering if you were to do, even the pencil code with polymer additives, which I think Dhruva has done, and Prasad, whether you end up seeing the same jets with the same
pencil code is not a good code for this kind of problems, but there are a lot of these open foam and all these other softwares like that can be used. But then, you are right, we change the concentration and then this curve would change. So that is also, for example, here magnetic field. If you change the magnetic field, then also this curve can change, right? So there are, you change the coronal temperature. Huh?
Fourth third is just an observation.
This fourth third is, we get this fourth third, but it has been established from Faraday excitation experiments, not jet formation. So the Faraday excitation, they mainly do to look at patterns, right? They are not so much worried about the jet formation, but we are showing here that even when you have jet formation, you still have this fourth third law. So whatever arguments they gave for the Faraday excitation also holds even in the jet formation case. What is? Oh, Fs. Okay, so we have normalized it. So Fs here is, I think it was, yeah, 2 point, or it was probably 3.3 millihertz, the 5-minute mode for the solar case. And for this case, I think it was something like 30 hertz, or I don't remember, 35 hertz, some way to normalize it so that, you know, we can compare them at the same footing. Huh. Huh. Why did we choose this? Yeah, because well, we thought that's the frequency, the natural frequency in case of the sun, and in case of the lab experiments also. Okay, yeah, there is one reason here. You see that there's a break in the this behavior here, and there is some physics related to that. So what happens below this 3.3 millihertz and what happens above? So that break is what is governing it here. And similar to that, here also you see that there is a break in the slope. So in both cases, we take this change in the slope as the frequency. And it so happens that here it is close to 30 hertz. It was not exactly that. Probably it was 35 or 40 hertz. And we just normalized it with that.
Because of the singularity on the interface, that will happen even if you don't have polymer, right?
That will happen even if you don't have polymer.
Like, why do we need polymer for these jets?
Yeah. So yes. So this is the next slide, and which basically says that we have a simulation with magnetic fields and the one where we don't have magnetic fields. And if you don't have magnetic fields, then what happens is the Kelvin-Helmholtz instability essentially breaks up the jets and it becomes really very turbulent. So the coherence of the jets is not preserved when you don't have the magnetic field. So that is the role that the magnetic field is playing. So, okay, so far we have now talked about the forcing. Now let us talk about the jet itself. What is causing the jet itself? Keeping the jet coherent. So here, so let me run the movie again, once again. So you see that here, the jets, they are basically following the magnetic field lines because that is what they have to do, whereas here they are not. And here is a plot that we prepared. So Shohel basically changed the magnetic field gradually. And then we found that from zero magnetic field to even a very small magnetic field, you see that the pattern becomes more and more anisotropic, right? So the role of the Maxwell stress or the magnetic field here is basically to provide anisotropy to this system here. Now, what is happening in the polymeric case? So this is an example of Faraday excitation in nature. So what this animal here is doing, it is submerging its back under the water and singing. It's basically a mating call, and it's singing at a frequency of around 20 hertz. And when it does, since it's water, it's forming these jets, but look at how much splashing is there, right? So these jets are basically forming droplets and they are breaking off. They are not coherent. Now, so this of course, you know that this is known as the plateau relay instability, which basically is pinching all the jets because of surface tension. We don't have surface tension in the sun, but we had Kelvin-Helmholtz there, which was forming vortices. So now if we add a little bit of a polymer to this fluid, And here in this experiment, what we do is we take the quasi-periodic P modes from the GOM data, which is a very old instrument, of which India was also a part actually, and we speed it up so that those frequencies would be in millihertz. So we speed it up in tens of hertz, and then we drive this Faraday excitation, and you see that what exactly happens is the polymer basically tries to hold the jet in place. It prevents the formation of the droplet. So that is why we need the viscoelasticity property here. So like the magnetic field was providing anisotropy in case of the solar plasma, the polymeric chains, when they are extending in the direction of the flow, is providing the viscoelastic stress or the anisotropy in case of the lab fluid. So that is basically, so you asked the question just at the right time. So this is quite well known. I probably don't have to show it here, that polymer addition suppresses droplet formation. So this is quite well known. So this is from a old paper. So you have this water jet, and you see that it breaks up into this atomizes into all these smaller droplets here. But if you add a little bit of a polymer, then it looks more and more glassy. So of course, we apply this very simple Maxwell pot model where the fluid is viscoelastic. So elastic because there are chains, and the viscosity is coming from this paddle here moving in a liquid of viscosity eta. So, and then of course you have a Deborah number, which is basically the ratio of the relaxation time of the fluid to the observation time, the amount of time you're looking at it. So if you look at the fluid for a long time, so Deborah number will be less than 0, less than 1, corresponds to viscous fluids. Whereas if you have large Deborah number, you become more and more elastic. So that is basically the idea of viscoelastic fluid in a very simple picture. So now this is also quite well known, has been studied, like I was telling Pallavi, for shear geometries. So the analogy between MHD approximation and what is known as the Oldroyd V model. So these are some of the papers written from an astrophysical point of view by this is Ogilvy and Mike Proctor. Both are in, and Dana Longkop in 2003, one from UK and one from US. So where they basically looked at this idea of viscoelasticity in the paper by Longkop looked at viscoelasticity and dynamo in the sun, the small scale dynamo in the sun, whereas Ogilvy and Proctor look at MRI. And basically the Oldroyd B model is characterized by these parameters here. So you have a solvent viscosity, you have a polymeric viscosity, and you have a relaxation time. So, and of course, there are some approximation, just as we have in MHD. The assumption is the spring, which is your polymer, is infinitely extensible. And the fact that your the polymeric fluid is dilute, which is the chain interactions, can be neglected. So the chains are only interacting with the solvent, not with themselves. So that is the idea. And then if you want to write down the Navier-Stokes equation for both cases, MHD and Oldroyd P, you will see that there are certain similarities. You can write down the pressure and the stress tensor in this way. And this has been written for incompressible fluid, but for the solar plasma, you can modify and write it, but you can see that there is a similarity. So basically what these people said was the long chain polymers interact with thermal fluctuations in the same way as the magnetic field is interacting with plasma turbulence. So just like the viscoelastic stress is due to the back reaction of the polymer chains on the solvent, the Maxwell stress is because of the back reaction of the magnetic field on the fluid, on the plasma, right? So there is this parallel here as well. And then if you write down the constitutive equations from the Oldroyd B model for the viscoelastic stress, and also you can write using the induction equation, you can write this equation for the Maxwell stress. So sigma m is the Maxwell stress and sigma p is the viscoelastic stress. So you see that the left hand side is very similar. The only difference is the right hand side. Now, if you take the relaxation time of the polymer to be infinity, which basically means that you go to more and more elastic limit of the viscoelasticity, then the Allred B model becomes equivalent to the MHD model when you put the resistivity to 0. So infinite magnetic Reynolds number is equivalent to an infinite Deborah number. So the Deborah number and magnetic Reynolds number have this, have this equal, can be used in equal footing, and this has been applied to Couette flow. So basically, to have a comparison, a parallel experiment, just like we did for MRI, the magnetorotational instability and the elastorotational instability. So this is a very interesting paper. They also worked with a similar viscoelastic fluid that we did. So there is this mathematical parallel, and then which means that we are on the correct track probably. But only difference with us is that we are not looking at a shearing geometry. We are looking at an extensional geometry because there's jets, right? So it is different from the shearing scenario here. So we are basically trying to explore it in the elongational geometry. So we try to write down the stress, what is known as the uniaxial extensional flow, the stress for that, for the polymeric fluid, and we find that it comes out to be a matrix like this, where so if this were a Newtonian fluid, then the stress would be just proportional to the strain rate. However, this is viscoelastic, so we have something known as a Troton number, which is the ratio of the elongational viscosity to the polymeric viscosity. So that is again dependent on the strain rate of the fluid in the viscoelastic fluid. So we have this Troton ratio. Now for Newtonian fluids, it is known that the Troton ratio is 3. However, for viscoelastic fluid which are under extension, the Troton ratio can be more than 1,000 or something like that. It could be like really large. So, and then correspondingly, you can also write the Maxwell stress, and then you can compare the eigenvalues of these matrices, and then we came up with this equivalence. That this is for a 2D geometry, of course, because we were doing 2D simulations. So we saw that this quantity here in the plasma is equivalent to this quantity in the viscoelastic fluid. The approximate value of the stresses in both cases have this sort of equivalence. Now, what do we do with this? So again, we did some back of the envelope calculations to find out the threshold for anisotropic stresses. So how large do these anisotropic stresses have to be so that the corresponding instabilities in both systems are suppressed? So in one system, it is Kelvin-Helmholtz instability, and in the other system, it is the Plateau-Rayleigh instability. So we basically try to find the strength of these anisotropic stresses. So in case of a plasma, we basically found that the inverse of the plasma beta, which is proportional to the magnetic field square, has to be greater than the square of the Mach number. So the magnetic field, so basically the square of the magnetic field in a non-dimensional form has to be greater than the square of the Mach number. So this is the limit of the threshold. So basically your magnetic field has to be greater than a certain threshold value. And here, so we did all sorts of estimates here, and we said the polymer concentration has to be greater than a certain thing, certain quantity here, which there are these physical values given in case of the polymer. So there are these microscopic values as well, like energy absorbed by each polymer molecule, and then this is the surface tension, number of droplets the jet can disintegrate into. So this concentration has to be greater than a certain critical value. So we have this threshold for magnetic field on one hand and another threshold on concentration. So basically now we try to do a bit more quantitative stuff, and we for the solar plasma case, we basically find that here we plot the number of vortices that you see in the Kelvin-Helmholtz vortices. The jets are breaking into as a function of the magnetic field. So you see there is a sharp decrease and then it plateaus. So basically it becomes very, very small. then this is some other measure of anisotropy that we came up with by just looking at images and analyzing how much anisotropy is there in that particular image. So there are these two different measures. So basically we did that to convince the referees that it's not just one measure, but you take any measure, you see the same kind of behavior with magnetic field. Similarly, in case of a polymer, we see that the number of droplets, they decrease drastically and then again level off. Again, for the polymers, we also defined another measure of turbulence. So basically, so since we were shining light on these things, jets, because we were taking it with a high-speed camera, we were shining light on it. So we could see how many bright spots we could see in the image, and that is a measure of turbulence. So this turbulence decreases as you have more and more coherent jets. So that is also a measure of that. So you see a very similar quantitative behavior of anisotropy. So now we have this fourth reason, which is anisotropy, fourth parallelism, which is anisotropy. So combining everything, we basically come across these four sufficient reasons for jet formation, ingredients for jet formation, which is gravity and fluid. And then you have large amplitude excitation and anisotropy. And in both cases, and if you have these, even though your two systems are widely disparate, you satisfy these four conditions, and then they are sufficient to form a forest of jets. So, so far we have just used this harmonic driving, right? So it is like artificial. I mean, okay, there is this 5-minute mode in the sun, but the sun also has solar convection. Now, from a solar physics point of view, we also have to prove that even though P modes can give rise to solar spicules, but can solar convection produce that kind of driving? So now what we do is, we instead of a driving, we put a realistic solar convection zone in the 2D model, and then we basically see it's the same model, we just add a solar convection zone below it, and then we check what happens. So basically, this is a movie of convection which Shohel has made, 3D convection actually. So you can see the solar surface undergoing all these, the granules are forming and breaking, and the surface is moving. So basically, there is this breathing of the surface that is taking place. And if you analyze it, you will see that the dominant mode is the 5-minute mode. So we go back to the 2D model, and then we see that, even if you have solar convection, no other external forcing, you can still produce these solar spicules, which have very good fidelity with the observed spicules. So this is the synthetic emission, the model synthetic emission from a model at 80,000 Kelvin, which mimics this silicon line observed by the IRIS spacecraft. And this is the extreme ultraviolet line seen by the SDO spacecraft. So we see that, the spicules look very, you can discern the spicules very nicely. And if we analyze more, we see that the spicules, they also follow a parabolic trajectory, just like they do in the observations. And we find that the distribution of spicule heights exists between, you see all sorts of spicules in this simulation with up from a lowermost to highermost, the maximum height. And this is similar to what we had in that very popular paint experiment. So there also the jets follow this parabolic trajectory. So if you look at the lifetimes here, this is in minutes, whereas the lifetime here was in milliseconds, 20 or 50 millisecond, right? Okay, so now we do something interesting
Simulation from which you were making the synthetic observation.
Yeah, this one.
That is 3D or 2D?
This is 2D. This is still 2D. Okay. This one I was just showing to motivate that the surface of the sun.
I see. Okay. Yeah.
Does this, but so far this is 2D. Okay, so this is still 2D because we can because we did several simulations and it was easier in 2D. So we insert some Lagrangian tracking tracer particles. So these are massless particles, and we just want to know what the plasma is doing. So we just insert them in the simulation. And these are colored by different physical quantities. On the left-hand side, I have colored it with vertical acceleration, whereas on the right-hand side, we have colored it with vertical velocity. So now you can see, if you can see this green, very focused fronts, which seem to be going up and then vanishing. So these are regions where there is really large vertical acceleration happening. So what is exactly happening here is there are these leaking P modes, right? So when the P modes are leaking out from the solar surface, they are being formed here and they're leaking out. They are interacting with the magnetic field and they're forming slow MHD modes. But since the solar atmosphere is stratified, as they propagate, these waves become shocks. They become steeper and steeper and they become shocks. And these also coincide with the shock fronts. The shock fronts are given in black here. Basically, we are looking for regions of compression, plasma compression. So in these fronts, the plasma is accelerated. And what is happening is there is an acceleration front. It is at some position. It is energizing the plasma at that position. Then it moves up. It has done its job. It moves up. So what does this plasma do, which has been energized? It also keeps moving up. Then this shock front energizes the plasma above and it keeps moving up and it goes up. So this is like a domino effect. So basically the shock front is moving and it is energizing the plasma in its wake. And that plasma is basically moving up. So you will see that these green fronts, and then you will see that there is these green regions where the vertical velocity is really large. So the green regions correspond to large vertical acceleration here and large vertical velocity here. So basically we find that now we spoke about these similarities between the fluid system and the plasma system. But here you see that in the fluid system, of course, we didn't have shocks, but we had surface gravity waves. So there, yeah.
Does this shock front coincide with Mach equal to 1?
Actually, more than 1. So I'll just show that time distance plot in a while to you. So there are because it's a stratified thing, but then we have checked that this RH conditions and all that, they work well in this inside these shocks here. So yeah, so in the fluid system, it was the surface gravity waves which were making these singularities of the surface, and then you were forming jets. Whereas in this case, there is also some kind of singularity, but in form of shocks. Because here the plasma is compressible, there it was incompressible. The fluid is incompressible. And also here we don't have the surface tension. So of course there are differences. So the exact physical mechanism in which the spicule is being energized and there the jet is forming is different. But yet you see there are very interesting similarities. So now if so this basically what we have done here is we have focused on one small region of that previous movie, and you see this acceleration front here, and we just follow it in time. So you see the acceleration front is moving up, and as the acceleration front is moving up, just below it a little spicule is being born, and then it becomes a mature spicule which has reached heights of 8 to 10 megameters. So this is how the spicule is being born. This is with increasing time, of course. And now if you look at your simulation from a vertical slit here, so this is what you will find. This is the time distance plot here. So these red regions are the regions of the shock, the propagation of the shock. And this dark blue region correspond to the regions where the Mach number is greater than 1. So you see, so these are also propagating upwards with a certain speed, which we find is slightly greater than the sound speed. So the sound speed characteristic is this black curve here. So the shock fronts are propagating slightly faster than the sound speed characteristic in the model, in our simulation. So next what we do is we look at two different regions. So you know these granules, so the granules, there are these downflow lanes, and then there's upflow, right? In a convective granule, the fluid is flowing down, and also it is upwelling somewhere else. So we find that near downflow lanes where your fluid is flowing downwards, so you see that there is some amount of squeezing happening here. So just as if you take a hose pipe and you squeeze, you will have a jet squirting out, right? So similar thing happens in this region. Whereas this is at the top of a granule. So here what is happening, the granule is breathing and it is kicking up the atmosphere above it. And here it is forming a certain, a spicule of a certain height. So these are two different mechanisms, both driven by convection, but there are slightly different things. But what it leads to is one leads to a longer spicule, one leads to a shorter spicule. And at least in this case, we found that if you plot a phase space velocity versus acceleration, you see that in case of over a granule, you see a sawtooth kind of a pattern in velocity and acceleration, which basically means that those spicules are getting a brutal kick, let me call it that, and those spicules are longer, whereas the spicules which are at the downflow lanes are getting a gentle kick because of the squeezing, and they are forming shorter spicules because here you see the acceleration is less. I mean, the positive acceleration is less than 10 times the solar gravity, whereas here the acceleration can reach as large as 30 times the solar gravity. So this we find from the Lagrangian tracking. So this is about the distribution of spicules that Rama was asking. So this is the height. We have not looked at velocity, but the height distribution as a function of a normalized sort of height. And we find that you have a whole spectrum. So we can say that the solar convection on its own can actually generate these strong acceleration fronts, and it will energize a forest of jets with this distribution. However, so we don't see any bimodality, we don't see any particular type 1 or type 2 where we can say this is being caused by this is being caused by that, but everything is appearing because of the solar convection. Now this was all in, okay, so this is what we learned from the Lagrangian tracking. So we see that these shocked regions, they coincide with regions of large positive vertical acceleration, which energizes the spicule plasma, which moves up. But once the plasma has been energized and the shock front has moved out of the domain, so there is nothing to energize it, so it's ballistic, the spicule moves back down. So, so what happens is, in a spicule, so it's not that the whole spicule is moving up and falling back at the same time. So it may so happen that the top part of the spicule is moving up, but the bottom part is falling back down because it's compressible, right? So there is a differential velocity inside the spicule. So this is a fine structure, and that is our prediction from a model, and we should try to observe it from, if we get high resolution observations in future, we should try to observe if this is the case or not. And we also conclude that solar convection by itself can generate all kinds of spicules and therefore a forest. Now, so after this, Shohel extended his work to 3D. And we have this convection happening, this I showed you before. And that also give rise to spicule-like features in the atmosphere. And this is in 3D. So this is a volume rendering of the volume rendering of the regions which are emitting at a wavelength of 80,000 Kelvin, corresponding to the silicon 4 line. Now, if you integrate along a line of sight, so we always, when we observe the sun, we always see images. We don't see the sun in 3D, right? So we always integrate the emission along a line of sight. So if you integrate this emission in a line of sight, it ends up looking like spicules like this. So from this kind of a simulation, we made this conjecture that the spicules need not be like conical jets. So they are more like these fluted sheets that you also see in auroras, for example. It's just an artifact of our line of integration. So in the solar context, such a thing has been proposed, for example, a long time ago, but people have challenged this. I mean, nobody has done any simulation, not from simulations, but they don't really believe this. But then we come back with a simulation where we actually see that it is still possible that the spicules are actually these plasma drapery or a curtain which is totally fluted. And yeah, so I just give a sneak peek of the 3D results because those are not published, so we are still fighting with the referee. And I'll thank you for your time. So this is the apparatus, the frugal apparatus that we used at home for our fluid experiments. And if you want to know more, I would invite you to kindly read this paper. So yeah, thank you for your time and for having me here.
The interesting talk. Yeah, we can take questions.
So in the first part of the talk, you're showing the images and the videos of the sun. What is the spatial resolution of the instruments that look at it so fast, as well as the spectral lines at such thick densities?
Okay, so the Hinode, I think the resolution is around 100 kilometers, right, Shahil? 170 kilometers. And I think the cadence was 5-second cadence of those movies that I showed you. Hinode, from Hinode. But Iris is little worse. So the hotter channels, the silicon channel, the resolution is little worse. Probably of the order of 150 kilometers or 200 kilometers, and because of that you cannot have such low cadence, because the cadence is actually related to your spatial resolution. If you have lower spatial resolution, you have to average even more to get this signal to noise ratio. So I think 20 second or something, Iris cadence is 20 second.
Thank you.
So in your solar experiment, by shaking it at the base, you're sending some energy in, and you have some open boundary condition at the top.
Yes, yes.
So how much energy goes out and how much comes back in?
So we don't allow much energy to come back in because there's a sponge layer. And in the driving, we try to make sure that the amount of energy is consistent with the observed, from the observation, we know what is the velocity amplitude on the photosphere. And we know this 3.3 millihertz or whatever it is. So you can calculate your energy flux, like half rho v square into something, into the acoustic, the sound speed. So we try to have, for most cases, we try to have that same, but then what happens, we cannot have it same for as observed, because we are doing this thresholding thing. So there our aim is not to keep the atmosphere hot or anything, or have the amount of flux same as observations. So there we just drive without any concern about the actual temperature that is there in the corona. But when we do this, so we do this experiment where we have a quasi-periodic P mode or something like that, with which we are driving. So if we do that, then we will try to match its amplitudes from the observed, and then the same amount of energy flux goes in.
Because in your lab experiment on the viscoelastic fluid, energy does not go out, it comes back in. So, but I guess that feature is not important.
Here the energy will only go out. So there is no, it's not, I mean, even in the fluid case, as I say, the surface gravity wave or capillary wave, whatever it is. So it's basically, it's sloshing, right? So it's there. But in this case, some of the plasma may be going out, but you have to keep in mind that the atmosphere is stratified. So the layer I'm driving is very dense, very heavy. So whatever goes out is actually very light. So what the spicules are actually much lighter, probably 500 times lighter than the photospheric plasma. So it's easier to excite them, right? So what is going out is much lighter than what I am moving. So there is loss, but not for a long time.
Like following upon that. So like, because of the magnetic field, that is also making things very anisotropic and so on. So does it also have an effect on like how much things can go further out? Because you were also talking about how this is connected to coronal heating, perhaps. So also his question that how much energy is leaving the domain.
You mean related to the strength of the magnetic field?
Yeah.
Yes, because if the strength is very weak, then this kind of driving is going to just make the magnetic field totally wound up and it doesn't look very vertical at the end of it. So I'm sure it affects, but we have not made those calculations about because this artificial driving. We didn't want to talk about coronal heating. So when we have realistic convection, that is when we will talk about the fluxes into the mass flux and things like that in the corona. The driving part is only to see if there are spicules, the forest of jets or no forest of jets. That was the idea.
Also, one more question I just had is that, you were saying how these can be sheets because you are seeing all these ridges in your Faraday plasma experiment, but Faraday liquid polymer liquid experiment.
Those cells.
But you still have to do 3D simulations to be sure of it, right?
Be sure of what? The spicule?
The idea that, these jets are actually
these cotton like yes, because how else will you have 2D sheets? 2D sheets is in the 3D domain, right? Whereas in 2D, when you have 2D, you only have these jets which are looking conical anyway. So there is no way to make any conclusion on the topology of those jets because it is 2D. Only in 3D we can.
Do you plan to do these 3D simulations?
3D simulations we have done.
Okay.
So from this, I did not show here, but I just provided a small that we have done this, and then this is a exciting thing that we get from this simulation also.
Nice. Any other questions? If not, we'll thank the speaker again. Thanks a lot for the really nice talk.